and we talk about the numerical model for dense granular flow.
Good morning, everybody. It's a pleasure for me to present the work we have done with Julien Chauchat, and I will talk about our experience about implementing a continuous numerical model based on the mu of rheology. Okay, so what are the tremendous problem is that there are several difficulties associated with the continuum model rheology. It has been discussed from this conference, but I will not address the physical point of view. I will only talk about the implementation issues. We would like and we will be interested to assess the domain validity from numerical point of view and also physical relevance, because we think that this continuum approach will be one of the tractable one for full 3D computations. So what are the problems? From physical point of view and theoretical aspect, many things have been done, but only very few attempts have been done from the computational point of view. There have been one of the works that has been discussed on Monday with Lydie Staron. They have convincingly addressed the column collapse. They have also addressed the problem with 2D flows, but nothing in 3D yet. So our starting point will be the tensorial approach, and we are going to see what are the key points to be addressed. So the first issue is to take into account for viscoplastic flows. In viscoplastic flows, you have the second invariant of the strain tensor that appears at the denominator. So from numerical point of view, when you want to address rigid body motion, you will get infinity. So infinity doesn't cast into a computer. So you have to deal with that. The other point is in the mu of I rheology, the pressure appears, but in a non-linear way, and moreover on the denominator. So what have been done for viscoplastic problems? There have been several algorithms that have been successfully proposed. The most computer demanding one, but also the most accurate one, is augmented Lagrangian from Glowinski. There are many works that have been done with that, but the problem is you have to compute both the strain and stress tensor. This means that it costs you twice the price of the other problem, the other approach. The other approach is based on regularization. This means that you will translate the singular problem into a continuous one. But now you enter with a numerical parameter that have to be tuned in order to recover the physical properties. And the other part, which was not addressed, was how to compute the pressure in order to get a positive definite pressure in an incompressible flow. Because unlike in the Navier-Stokes equation, not only the pressure gradient is required, but also the pressure itself. So it is a little bit tricky for people dealing with incompressible flow, because most of them deal with Navier-Stokes equations, incompressible Navier-Stokes equation. And when you, whatever the two main family of approaches, the fully coupled velocity pressure or the explicitly decoupled velocity pressure, in both cases, the pressure you end up with is not positive definite. And you have an integration constant also that enter the game. And the problem is, what about this integration constant? So I will not enter into details, but this is a crucial point to be addressed. Our starting point was the work of Job and co-workers. So we start with an incompressible flow approach. Here you have the momentum equation. For notation, I just recall the quantities. Here are the physical point of view. Now, how do you derive the numerical implementation? You have several. We have chosen to address the regularization approach. So we have translated what was done for Bingham viscoplastic flows into a mu-phi approach. So in the literature, there were three main class of regularization, and both differ from the way you change the denominator in order to reach a continuous model in order to tackle the singularity. So this one was popular in finite element because you can get the Jacobian. You are able to derive formally the approach. This one was also popular, but it is not longer regularized in the way that you still have a singular denominator. So we have ended up proposing an approach which is very close to Berkovian-Goldman approach. For finite elements, it's a better one, and we have just adapted to mu-phi approach. I will not enter into the detail of the functional analysis, but what we have to ensure is a good compatibility between velocity and pressure space of approximation, and we are looking for finite dimensional space, and we would like to get this functional space to behave in the well way, and also to be continuous and once continuously derivable. So what the main purpose is to get a fully consistent incremental approach. This means that we have to compute a Jacobian of the full functional. This means this Jacobian is a functional derivative of the previous weak form. For notation, it is written here. You can see that there are many terms, and those terms are likely to be awkward. In order to get a good numerical behavior, we had to modify the pressure, because as I told you previously, from the classical incompressible flow solver, it is not positive definite. So we have changed the pressure in order to render it pressure positive definite. Okay, so the pressure and also its derivative. So now, what about the validations? We have considered analytical solution from where we are able to compute the accuracy of the model, and also the order of convergence, because it's important to know which price we will have to pay for a full 3D computation, and also from Job and co-workers experiments. The first analytical solution is the vertical shoot flow between rough end walls. It's a 2D problem for which it was inspired from the Bingham flow, 2D Bingham flow, but it is written for the mu-phi rheology. So we end up with a very comparable solution as the Bingham flow. And now here are the different implementation of the regularization technique I showed you previously. Hopefully, both of them are able to recover the analytical solution, but what you can see, whatever been the non-dimensional velocity, inertial number, velocity gradient, or viscous stress, but what you can see from the convergence analysis, spatial convergence analysis, that the different way you will change the singularity into a continuous approach changes the end accuracy of the model. So both have not the same behavior from computational point of view. The one we have proposed is roughly equivalent from the previous in the beginning, but it is a little bit better at the end. So we have chosen this one, and now since we have two numerical tuning parameters, the one for the penalization to recover the pressure, and the one from the regularization to recover a continuous viscosity, we can see that both are converging versus spatial discretization. This means that we can get optimal convergence rates depending on those coefficients. Another very popular 2D model is the Bagnall flow. Here again, we get the analytical solution. I just show you the regularization we have proposed. Here again, we are also able to show very good convergence analysis. And moreover, we have been very interested also to show that we are able to find out the limit tilt angle below which there is no more flow. But here, the normal flow is numerical accuracy under which we will consider this is no flow. So it's very slow creeping flow, but there is a flow even in the rigid solution. Here are the comparison versus the experiments of Job. It is a flow over an inclined plane with lateral wall effects. The dots are the experimental point from Job and coworkers. The blue line were computation performed by Pierre Job, and the dashed line are the computation we have done, but we have different boundary conditions. We can see a very good agreement for three non-dimensional flow rates. Here are the velocity versus the span-wise direction. Here are the flowing depths versus the span-wide direction for the three flow rates, non-dimensional flow rates. You can see a quite good agreement, except close to the boundaries where there are something to do. Now, another numerical experiment is the flow over a horizontal cylinder driven by gravity. Here you can see the drag force, non-dimensional drag force versus the fluid number. Here again, you can see this point is a very teeny value. Here again, this is a close-up. So the drag force increases versus the fluid number, but until this point, this is purely artificial flow. It's the creeping flow induced by the numerical regularization. It should be no flow before this value. Above this value, the drag force increases and turns to a kind of asymptotic. We have plotted here the drag coefficient versus modified fluid number and compare with experiment from Sheata. And you can see that the trend is quite good, but we have here again to tune a kind of numerical parameter in order to get the right values. But even in Sheata experiments, you can see a quite large discrepancy between experiment to experiment. But the trend is there. If you compute the fields for the pressure field, the velocity field in the stream-one direction, and the velocity field in the crosswise or span-wise direction, you can see that you have rigid body motion, and you have zones very close to the cylinder where there is no more flow in the upwind direction and also in the downward stagnation point. Okay. Here a close-up. Here is the regularized pressure. You can see everything looks fine except in the transition where the pressure change sign and where the regularization of the pressure has a little influence. But for the flow in both directions, the solution is quite continuous. So we were pleased with that. Now we can access to more depth into what are the main ingredients of the mu of I rheology. We can get the contribution of the static component, the dynamical component for this flow, and the particulate viscosity map. And you can see that everything is localized very close to the cylinder, and each map has been done for two driving gravity. But nevertheless, it's interesting to understand what happened very close to the kind of localization bounds close to the cylinder. So now to conclude my talk, I have shown you a quite successful implementation of the mu of I rheology, but nevertheless there remain some problems. The problems are that this approach up to now fails to provide quantitative agreement versus very sensitive quantity, pressure sensitive quantity, as for example the lift. We have made some attempt to compute the experiment of François Guillard that was discussed yesterday, and the drag force is correctly reproduced. Nevertheless, the lift force is not. So it is not yet satisfactory. And the reason why it is not satisfactory is we have understood that the approach we have followed in what I have discussed here is the first one. You have a penalization approach from which the pressure is recovered from the divergence of the velocity. Since it is not positive definite, we have regularized in this way, but it is not satisfactory. The way we think that would be better would be to get a nonlinear Lagrange multiplier of the divergence, which write this way. I have not yet implemented this approach because it touches the core of the solver, which is a tricky part. So you have to rewrite the way you compute the pressure, which is very deep in the code. But what we intend to do after that will be successfully addressed will be to attempt to compare the two approaches on the very sensitive problem, such as the lift on immersed body in gravity, hydrostatic gravity, and for cylinder, but also for the full 3D problem around spheres. there are also several other limits that have been to be overcome. In the first approach, we have used variable volume density, which is no longer satisfactory for flow around obstacles. We have seen that just behind the obstacle, it is evident that volume fraction is no longer constant. So this assumption has to be overcome. And also, we have seen interesting work dealing with the way to complement the mu of I rheology with non-local effects. Okay, thank you for attention.
Questions?
This experiment of velocity field around the cylinder show that the velocity field far from the cylinder decays roughly exponentially with the distance.
Yeah.
Does this code reproduce this trend?
We have not checked, but we have to do. If I can get back. Yeah, at the moment, we have considered no slip boundary condition, but we have also tried to introduce some kind of friction coefficient in order to...
Far from the cylinder, not at the cylinder, but...
Yes, also at the cylinder, because when you deal with the continuous approach, you have, let's say, half the diameter of the particle, which is not seen as a good kinematics. So provided this adjustment, if you leave some friction stress on the rigid object, you will get the right velocity profile.
Physically, you talk, it's a big problem that the pressure is non-positive, but that's a physical phenomenon. When normally in liquids, when the pressure becomes negative, it can happen in liquids through cohesion, but or you get cavitation.
Yeah.
And lots of granular flows, you expect to see that. So, aren't you throwing away some physics with this? And then there's also a problem on any free surface with this rheology that I is going to go to infinity. So you're going to get a very narrow boundary layer. I was wondering how you dealt with that.
To come back to the first question, pressure can never be negative, as everybody knows.
Then it cavitates.
Yes, but it goes to zero, but never negative. Okay? Negative pressure.
Depends on your reference.
Yeah, of course. But nevertheless, what I mean with the positive definite pressure, the pressure you end up from an incompressible flow solver is not a physical pressure. It's a pressure that satisfies the continuity equation. This means that the pressure that satisfies divergence V equals 0. Nothing else. But it's not
But you're
physical.
not solving the divergence of the momentum equation. You're just, right.
But you cannot do anything more with this kind of approach.
Well, why can't you solve the divergence of the momentum equation?
Yeah.
And then the process.
Then you have to apply boundary condition because you end up with a Poisson-Laplace equation. So in order to numerically solve this equation, you need boundary conditions. But those boundary conditions are no longer consistent with the minimization of the total energy of the system, because from minimization approximation, you cannot apply both velocity and pressure at the same place.
Okay, I think last question.
Okay, so you think the problems, numerical problems, are coming because you're expressing the viscosity in terms of the pressure and the strain rate, and the strain rate can go to 0 and so on. But if you use the equivalent Bagnall laws, where you express all components of the stress in terms of the strain rate of strain tensor, then there should be no problem with the regularization.
Yes, but as I told, you have to compute both the stress and strain tensor, because you have a yielding problem. So this costs you twice the price. For 3D, you cannot afford that. But you can do that. What Glowinski and coworker does, but only for 2D problems. For 3D, if you want to get a huge spatial resolution as you need close to the sharing boundaries, you can no longer tackle this problem with this kind of approach. But you can do it. You're right.
Okay. Thank you very much.